not accounting for, but how many of us would, if I weren't to ask you to calculate it, what time would you guys leave? I'm hearing 8. Yeah, you'd leave about 8. Because you know what? Let's actually look at the problem a little bit. We know that we're going to travel about 100 or about 60 miles an hour, right? On average. I still have to stop and go because I'm going to hit the stoplight out at leaving here in Enid, right? I'm going to hit the stoplight. Probably going to have to, and once I get to Edmond, we all know what traffic's like at Edmond, right? We got traffic that's a little bit difficult. So we're going to round up, right? We're going to say it's 120 miles. And this is actually point to point. It's actually centered at the Google. This is Google Maps' distance as you drive by car, the traditional route, 412 to I-35, straight down I-35 to Norman. That's the route that I used for the 117 miles. So it's about 120 miles, 60 miles an hour. It's going to take us about 2 hours. If we want to be there by 10, we got to leave by 8. That's a calculation we do all the time, right? It's a calculation we do all the time. But it's not any different when we do it for physics. It's not any different. So I'm going to actually work through it so you guys can actually see it. But before I do that, I've got to log on to Blackboard here so I can show you that you have your first quiz. So you know where it is. So you do your My Courses thing. You do your quiz, your general physics thing. You go to course materials, and you go to week 2, and there it is. It's right there. The lecture from Wednesday is also right there, and it links to YouTube. So hopefully it closed captioned. I don't know if it did or not. I didn't get a chance to look at it. But that's Wednesday's lecture. I will warn you that sometimes the lecture captures with a little black box, and I think Wednesday's lecture captured with a little black box in the upper right corner or upper left corner. And what that is, it's a setting on the lecture capture system, and I forgot to check it in the computer on Tonkawa, so it gave me, and that's a picture-in-picture kind of setting. I think I've got it set up so that it won't do that over here today, but just as an FYI, that's what's causing that. It's not something wrong with your computer. So the quiz is right there. You have 2 opportunities to take the quiz. Highest score will be the one that gets recorded, and the quiz is due at class time on Wednesday. Okay, quiz is due at class time on Wednesday. So that's where we're at. No, it is not timed. I don't time my quizzes. The only thing that will be timed in class is the actual test. And the actual test, I will not do, even though our time is lengthened. It's not just a regular hour long. You will have the entire class period time to do the test. So, although I will set it up to be an hour test. So that's how I set them up, and but you will have the whole time to do it. So hopefully time pressure will not be an issue for anybody. All right, so now I want to go see if we can get things to work appropriately. All right. So everybody see the document camera? You see the document camera over in Tonkawa? Okay, we're going to give it a whirl. All right, so let's look at this problem. And I'm actually going to set this up so that you guys can actually see it. So basically, if I'm driving, I drive to I-35, and I drive down. And lucky for us, this is pretty much, a right triangle, even though we've got it absolutely as a right triangle. And we've said that this length and this length combined, so x plus y is going to equal 117 miles. We said we have an average speed of 60 miles per hour. And so the first thing we got to figure out is how long it's going to take us. Okay? First thing we got to figure out is how long it's going to take us. So if I do that, I'm going to do my 60 miles per hour. Oh, no, I don't want to do it that way. I want to do 117 miles. And I'm going to put my 1 over 60 because I want miles on the bottom, hours on top. And I plug that into the calculator, I get 1.95 hours. But I want to figure this out on a digital clock, so I need to know what that minutes are. So 0.95 hour. There are 60 minutes in 1 hour. And if I work that out, it's like 57 minutes. So it's going to take me 1 hour and 57 minutes. So if I want to be there at 10 a.m., I'm going to have to go 1 hour, that's 9 a.m. I have to go 57 minutes, and that gets me to 8:03 a.m. Now, there are other ways you can do it, of course. That's what's really nice about these things. There are other ways you can do it. But we can come back, and we will come back to our lovely triangle here in a little bit. Okay, so a couple tools for you. By the end of the semester, if I were to write myself a physics cheat sheet, this is what it would look like. So this is an equation sheet that has all of the equations that we end up using in General Physics 1. It has my triangle in here. It's got my x squared plus y squared. My square root of that gives me my radius. It has my conversions back for my trigonometry. It has all what we're going to call our kinematics, and we're going to start kinematics today. So we've got all of that type of information. It's got my force information. It's got work information. So if I were to really write up a equation sheet, this would be my equation sheet that I would write up. Because what I haven't told you is you guys get to have a cheat sheet for the test. Okay, 1/2 of an 8.5 by 11 piece of paper. Anything you want to write on it, you can. My only criteria is it has to be in your own handwriting. Okay, not typed. It has to be in your own handwriting. There's a rationale for my madness, but 1/2 of an 8.5 by 11 sheet of paper, you can have anything you want to on it. Okay. Just as a reminder, some basic information that from your algebra text, if you wanted to have it, you can use it. It's in the appendix. One of the challenges that people had on the homework is that you had a 2-equation to unknown problem, right? You had a 2-equation to unknown problem. So that's one of the difficulties that we have, is that we are going to be using 2 equations to unknowns a lot. So I would suggest, if that's one of those areas you want to brush up on, dust off your algebra book, or go to OpenStax and look at the algebra book in OpenStax to look at methods for 2 equations to unknowns. If I want to solve an equation that has a square to it, remember the quadratic formula. That's really going to help you out. Okay? Really going to help you out. My equation for a line, y is equal to mx plus b. Remember, I can substitute anything in for y and anything in for x, but my m is my slope and b is my y-intercept. Slope is the rise over the run, or the change in y over the change in x. Distance between 2 points, if I give you 2 points, like what we've been working with in vectors, and I know their x and y component system, I can actually calculate it. So this is a handy-dandy set of tools for you as well. These are kind of just some mathematics. Here's my good old trigonometry stuff. There's my tangent. Here's another tangent. There's a sine, and the cosine is equal to 1. Some of my angles in a right triangle is going to be 90 degrees. So you get a lot of handy-dandy pieces of information. So this is another useful tool for you. So where we ended up on Wednesday is we were doing vectors. Okay? We were doing vectors. And we were talking about the fact that I could do things head to tail and add it head to tail. So one of the things I can do is I can travel with a vector here. And this vector is going to be 3 paces. So I'm going to walk 3 paces. And then I'm going to make a turn. And now I'm going to walk 6 paces. And this angle right here is 30 degrees. Then I'm going to make another turn. And I'm going to give myself a point of reference. I'm going to make another turn. And I'm going to walk 5 paces. So I did not do this to scale, but I've drawn it so it's going to kind of be to scale. And I want to know the resulting distance. I want to know the resulting spot where I was. Oh, I didn't draw it very well. So I'm going to go ahead and extend this one out just a little bit. So I want to know the resulting distance that I traveled, or the change in distance, or the change in position that I traveled. So I want to know about this vector. I can do this graphically. I can take a protractor and actually do it graphically and come up with the exact same answer. I add vectors head to tail. Vectors have direction and magnitude, so I can do it that way, but I can also do it mathematically. So let's call this one vector A. We'll call this one vector B. And this one vector C. And where we were on Friday or on Wednesday was I said, all right, I can write vector A, and vector A in this case is 3 paces because everything's in the same units, and it's only in the x direction. So it's going to use, I'm going to use that unit vector with the I hat to give me that representation of the vector. My vector B, and this is where I can use my sine and cosine to help me out. So if I put in my right triangle here, my x portion of that vector is going to be 6 times the cosine of the angle in the I direction, because this is my adjacent side, this is my opposite side, plus 6 times the sine of the angle, which is 30 degrees, in my y direction. I can do the same thing with my vector C. Okay, there's my vector C. See, I'm using the black. So vector C, it's going to be 5 cosine of the angle, and in this case that's 60 degrees in the I direction. But this vector is going downward, so I want to make sure I have a negative sign. So I keep track of my directions correctly. I want to make sure I have a negative sign. I could do it a couple of ways. I could use the sine of I can use the negative sine of 60, or I can use the sine of negative 60. And if I look back at my little trigonometric identities, it turns out that my sine of the negative angle is a negative sign, so it just depended on which way you wanted to do it. You can do it both ways. But this is going to be 5 sine 60 degrees, and that's in the j direction. So if I plug this into the calculator so that I have this, okay, so I've got A is 3I, B I'm plugging it into the calculator. It's 6 times the cosine of 30, and that ends up being 5.196i. And 6 times the sine of 30 ends up being 3j. And my vector c, when I put it into the calculator, I get 5 times the cosine of 60, which is 2.5i, minus 5 times the sine of 60, which ends up being a negative 4.33j. Now I can add these up to get my resulting vector. So I'm going to add 3 to 5 to 2.5. This gives me 10.7. And 3 minus 4.33 gives me a negative 1.33j. So if I had this on a piece of graph paper and I've done this to scale, this vector in the x direction, if I look at my individual components, will be at 10.7, and it'll be at minus 1.3 in the y direction. So it'll be below the horizontal. Now, if I want to figure out the magnitude of that vector, how long is that vector, I'll find out that magnitude. I take the square root of 10.7 squared plus negative 1.33 squared. And I plug that into the calculator, do the square root, I get 10.8. So if all these paces were uniform, that vector is going to have a length of 10.8 paces. And I can figure out the angle by doing the tangent of the angle is equal to minus 1.33 divided by 10.7. Do the arc tangent of the angle, and it says it's a negative 7.1 degrees. Yeah.
What does the r stand for when it's not inside the absolute value?
That's the resultant vector. This is this vector here. This is r. That's the vector we're trying to figure out. That's why I color-coded it. And r, the magnitude, that just tells me how long it is. It's an absolute value. Because remember, vectors have direction and magnitude. So we can do this to solve a couple things. You can play with it a little bit. So let's look at our Enid de Norman problem. So my Enid de Norman problem was, I'm going to go this way, and I'm going to go this way. And as the crow flies, if I could go straight that way, like a crow, and actually fly that way, as the crow flies, if you go out on Google Earth or whatever, you find out that this vector right here is 84.7 miles. But I had to travel in the x direction and I had to travel in the y direction to get there. And x plus y is equal to 117. Okay? And it turns out, if I do this r is going to equal the square root of x squared plus y squared. But I know r, 84.7, is equal to the square root of x squared plus y squared. I now want to know what x is, and I now want to know what y is. Okay, for you Enid people who happen to travel towards I-35, what is the approximate distance from Enid to I-35? Is it 30 miles? That's about 30 miles. Okay, so we have a number, and this is one of those cases where we're going to do two equations, two unknowns, but we actually have a pretty good figure of what that number should be looking like. Now, granted, we're making a couple of assumptions here. We're making an assumption that this is actually a right triangle. It's not quite perfect, right? The road's kind of not quite perfect right triangle, but it's close. So I'm going to solve two equations, two unknowns, and I'm going to use this as an example because we know this and we know what the sum is. So let's figure it out. So if I do this, I'm going to get, and I didn't actually do this before class. So we're going to square this one. So if I square 84.7 and I square it, this gives me 7174 about x squared plus y squared. And I have 117 is equal to x plus y. We're going to brute force it. Okay, we're going to brute force it. There are other mathematical tricks that we could do, but we're going to brute force it. So I'm going to solve this one for x. So x is going to equal 117 minus y. All I did is move the y to the other side, and I've got x. Now I'm going to square x. So x squared is 117 minus y. And it's 117 minus y. Good old algebra, right? So I'm going to do this. I'm going to do this and this. So I get 117 squared. So I'm going to actually calculate it, so I don't have to carry that around. That's going to be 13,689. And that side is plus y squared, right? Now I'm going to do this, and I'm going to do that. So I get minus 117y minus 117y. Gives me, so this actually equals 13,809 plus y squared minus 234y. Everybody with me so far? Haven't done anything? Well, guess what I can do is I can take this x squared, plug it in there. So now I can do this. So I have 7174 is equal to 13,689 plus y squared minus 234y plus y squared, because I have this extra y squared. Okay, so now I've got 13,689 plus 2y squared minus 234y is equal to 7,774. I'm going to put everything on the side, and I'm going to rearrange it just a little bit. So I've got 0 equals, this is my 13,689 minus 7,174 plus 2y squared minus 234y. Plug it in the calculator. Okay, now I'm going to rearrange it to put my y squared first. So I get 2y squared minus 234y plus 6515. It's equal to 0. We can use our quadratic equation. A is equal to 2, B is equal to minus 234, and C is equal to 6515. So I've got minus B plus or minus the square root of B squared minus 4AC divided by 2A. I plug in my numbers. I get a minus 234 plus or minus the square root of minus 234 squared minus 4. A is 2, C is my 6515 divided by 2A is 4. because a was 2. So I've got 234 plus or minus the square root of 234 squared. Okay, so it's 234 squared plus, or go back, minus 4 times 2 times 6515. And if I put it in the calculator right, this is 2636 divided by 4. Take the square root of that. Sure, just a second. So I got 234 plus or minus 51 divided by 4. So I have 2 possible solutions, because I had a square, so I had 2 possible solutions. So if I do the 234 plus the 51 divided by 4, one solution is 71.25. The other solution is 234 minus 51. Divided by 4 is 45.75. And since we have some knowledge, about that one side, which answer are we going to pick? From 412 down to Norman.
No, 71.
Yeah, we're probably going to pick the 71, right? We're probably going to pick the 71 because we have some knowledge of that. Okay? We have some knowledge of that. We're probably going to pick the 71. So if I'm going to do that, I'm going to take my 117 minus my 71.25. If I do that, 171 minus 71.25, it gives me 45.5. Now again, we didn't use an actual, so these answers are actually my x and my y, right? In this case, they are my x and my y. This one happens to be what we would use as x. That one's the one we happen to use as y because we have some knowledge of the fact that that's where we're at. And remember, it's not perfect, okay? But our 45 is in the same ballpark as 30. And we don't have a perfectly right triangle. But we can actually use it to help us out to do some frames of reference. Okay, 2 equations, 2 unknowns. This was the brute force method. Sometimes you can do other things to do it, other tricks you can apply. But this is a brute force method. So you guys had a 2 equations, 2 unknown problem in the homework. You had the mountain problem, right? So in my mountain problem, I had a person that was here. I had one angle. Then came a little later, had another angle. We wanted to find H, right? This was a distance X. We were given that distance, that's phi, okay? We were given that distance. So in one case, the tangent of the angle was going to be h over x. And in one case, the tangent of the angle is going to be h x minus d. I don't know x, and I don't know h. But what I can do is solve for h, or solve for x. So I'm going to do x is equal to the tangent. Let's do this. X tangent is equal to h. Okay. I want to solve for x, so x is going to equal h divided by the tangent. And now I can plug that back into here. So I get the tangent of phi is equal to h divided by the tangent of theta minus d. Now it's just algebra. Because I know d, I know phi, or theta, and I know phi. And I have several ways to approach the problem. Your text recommends, your text recommends to go ahead and carry it out and actually solve for h before you plug in any numbers. There is some advantage to that because then I can plug in any angle I want to and solve the problem. But there's also some advantage to go ahead and carrying it through. I can figure out what the tangent of my angle is and figure out what the tangent of my angle is, and I already know what d is, and it may be a little easier to manipulate with the numbers. It's whatever makes sense for you. It's a little harder to figure out where you went wrong by punching it into the calculator if you do it the other way, where you punch in your numbers, but sometimes it makes it cleaner on your piece of paper. So it's just up to you which way you want to do it, so that you can actually kind of move along with that. All right, so we're going to work a problem. So here's our problem. We've got a surveyor. I'm going to write it out, and then we got a surveyor measures the distance across a straight river using a tree on the opposite bank. As a reference, he walks along the bank for 150 meters, and then he sights the tree at a 32-degree angle. This is a symbol for angle, by the way. When I turn it, you'll see it a little better. And we want to know how wide the river is. Okay, so surveyors measuring the distance across the straight river using a tree on the opposite bank as a reference. He walks along the bank for 150 meters, and then he goes back and he looks at that tree, and it's at 32 degrees. So how you work the problem and the methodology for these problems, and I think it's like around, let me see, it's around page 18 about solving physics problems, somewhere along the way. I think that's in the old text, but the new text, it's right in that spot. It tells you to first read the problem. Sometimes it does help to read the problem out loud, okay? Because that gives you an opportunity to hear it. So, read the problem. The second thing you do, particularly on physics problem, is draw a picture. When in doubt, draw a picture. All right, so what we've got is we're talking about a straight river. So I'm going to draw a straight river. So there's my straight river. We know we've got a tree as a reference, so here's my tree as a reference. And we got my little surveyor person over here, and there's our straight line across the river. We also know that we're going to travel 150 meters this way, or it could travel 150 meters the other way, or you could draw your picture just like this. The orientation doesn't really matter in this problem, so whatever makes sense to you. And then we're going to sight the tree, and we're told that this is 32 degrees. So the third part is label your picture. Now I labeled it as I went. When I drew my picture, I labeled it. We want to know how wide the river is. So this is the part we're trying to figure out. Okay, that's the part we're trying to figure out. So, I got a toolkit. I know that the sine of an angle is the opposite over the hypotenuse. Well, I don't know the hypotenuse. I do want the opposite, and I have an angle, but I don't know this one. So that's probably not the one I'm going to use. I can do the cosine. Okay, cosine adjacent over the hypotenuse. Well, I know the adjacent, and I know the sine, so I could figure out the hypotenuse. But that's probably not the one I want, because the tangent is going to get me directly there. The tangent is the opposite over the adjacent. This is what I want to know. That's what our question is. And this is known. So I'm probably going to use the tangent. It's a nice way for me to be able to get there directly. Because I do know the angle. So I've got the tangent of 32 degrees is going to equal what I want to know. And that's the opposite over, that's why I use opposite. Because this case I used x as my variable. And I know the adjacent is 150 meters. So this is going to be 150 meters times my angle. And if I plug that into the calculator, it's like 94 meters. So I didn't have to cross the river in order to figure this out. Didn't have to take a big tape measure in order to figure this out. I could actually use the information that I have. Okay, I couldn't quite hear it. You were asking how far what? That's true. This distance that I measure, or this distance that I estimated, is using that tree as a reference, but the tree could be exactly on the bank. I can do all kinds of reference points, but it's an approach to the problem. Okay. So we're now done with chapter 1. We even sort of started chapter 2. Because let's look at my good old Enid problem again. My Enid de Norman problem. Okay? My Enid de Norman problem. So I've got my right triangle, because we're approximating it as a right triangle. Right? And we've now said that this is about 45. This is about 71. But we also said this right here was 84.7. Okay. You guys did the first lab. Everybody's done the first lab, where you guys looked at position versus time and change it, and velocity versus time. We have something that are vector quantities. Everything that we have on this picture is a vector. Okay? Everything that we have on this picture is a vector. So if I'm starting here and I'm finishing here, I can do something that's a change of position. Okay? That's a change of position. And my change in position is going to look at my position initial, and I'm going to use x just for right now, minus my position, or my position final minus my position initial. So subscripts are going to help you. Subscripts are going to help you. So my change in position depends on my stop point and my start point. And you can see that my change in position is not my distance traveled. My distance traveled, if I'm in the car, is 117 miles. This is distance traveled. This is change in position. And my change in position is 84.7 miles. Those two things are not the same. Okay? Those two things are not the same. We're going to go ahead and use 2 hours. Okay? We're going to use 2 hours because that's kind of what we calculated if we're traveling at an average of 60 miles per hour. So if my time to travel this is 2 hours, if I calculate distance traveled versus over time, this is going to give me a value of 117 divided by 2, and this is going to be miles per hour, so I have my units. And if I do that, that's 58.5 miles per hour. But if I do position or change in position versus time, that's my 117, or that one's my 84.7 divided by my 2 hours. And that gives me 42.35 miles per hour. Okay. Distance divided by time, and this is where we're going to get really persnickety in physics, and then I'm going to go ahead and mix things up, and we'll actually use the terms interchangeably again. This is speed. This is velocity. This has direction and magnitude. This is just a calculation. This has direction and magnitude. This has just a calculation. Speed and velocity aren't the same thing. Now, a lot of times, speed and velocity is the same thing. Like if I'm traveling in one dimension. Okay, if I'm just traveling down the road here, I start here, and I end up here, distance traveled, and the velocity are the same. But if I do the swimming pool thing, okay, so I'm doing laps in a swimming pool, so I can go back here and back here. My position, my change in position stayed the same, but my distance traveled ended up being 3 times. Because I went up, back, up. So speed's going to be related to distance versus time, and this is distance traveled, and my change is going to be related to my change in time. So basically what we're looking at is our start and stops, and we have to be careful if we want to calculate an average. So what we've got so far is we're going to use X to represent position. I mean, we now know that velocity is a vector quantity. We usually use a little arrow on there to represent that it's a vector quantity. And it's defined as the change in position divided by the change in time. Or I can have x final minus x initial is equal to t over t final minus t initial, and that gives me my velocity. Now in this case we're only traveling in the x direction because I'm only in one dimension. And how we end up working in physics is we end up in one dimension and then we expand it to other dimensions. So we're in one dimension and I've got a change in position with respect to change in time. One of the things you guys did in lab is you also looked at and you found an acceleration. And my acceleration is my change in velocity with respect to time. So this is going to be my velocity final minus my velocity initial divided by my time final minus my time initial. Let's look at some units. So if I'm in SI units, this is in meters per second. This is in meters per second divided by seconds gives me meters per second squared. So that's how we manipulate our units. A is, in this case, is acceleration. Yeah. So this is velocity, and this is acceleration. Okay. I've got velocity and acceleration. Both are vector quantities. Okay. We got some key things that we want to look at. So in the lab you guys did, I could do position, and I could do time. Okay? And let's say what we did in the lab is we walked at a constant velocity for a little ways. Then we might have stayed in place. And then we might have decided we were going to do a little acceleration. So I have a curve here. And I might have gotten a graph that looked like that. Okay? This point, because I get a straight line, the straight line is going to tell me that I'm traveling at a constant velocity. This line where I'm not changing position, we know something about my velocity. My velocity is 0. If I'm not going anywhere, I'm not changing position. And if I'm not changing position, my change in position divided by my change in time, that's 0 divided by t. I'm not going anywhere. Okay? This one, if I ended up plotting it as a velocity versus time graph, this might have ended up being a straight line. If I have a straight line here, I'm traveling at a constant acceleration. Okay, so my straight line on a velocity versus time graph is going to be a constant acceleration. Straight line on a position versus time graph is going to be a constant velocity. So let's kind of look at this a little bit more. So now I have a position versus time graph. I'm actually going to put some numbers to it. This is in seconds. This is going to be in meters. And this is 1, 2, 3. And I'm going to do, we're going to do this, okay. So I've plotted my data, and since it's data, it's not exactly, I've done an approximate, through my line. Okay. When we plot data, and if we're hand plotting it, we draw our line through there. If we start at 0, okay, it's very much like looking at my little car. In fact, if I could do this, I've got my little car here. I'm going to use a little Dr. Seussy car. We start at 0. And at 1 second, my little car, this is going to be 1 meter, this will be 2 meters, this will be 3 meters. We're going to end up here at 3 meters based on how my graph was. This was a little, no, this is at 2 meters, sorry. So we end up at 2 meters. I'm going to do a half. And let's see if that's a half. That would be a 1 meter. So in this case, my car at 1 second is kind of right here. and I took my data there, and my car is like right here, and I took my data right about here. There's my car. And I plotted my car, actually just did the plots, took data. When I draw my line through a data, I don't connect the dots. This isn't a dot-to-dot connection. My straight line is going to be an approximation of the data, and I can draw a straight line through it. But for the most part, this is a constant velocity. So the fact that I have a straight line tells me I have a constant velocity. Equation for a straight line, because we all learned it in algebra, y is equal to mx plus b. That's my equation for a straight line. Well, in this case, y isn't, this is just an arbitrary y. In this case, y is actually position. I got mt plus b, because this is my time. So my x-axis is time, my y-axis is x, so I could rewrite my line as that equation right there. Now, we can go in here. I'm going to do, let's do it. So I'm going to go in here, and I'm going to actually, we'll do it this, there we go. Okay. So I'm going to figure out the slope of this line. Okay. This is kind of like at 0.8, and this is 2. And that's at 1, and that's at 3. So that's good. So now if I do the slope, slope is going to be the rise over the run, or if I do it in my good old algebra form, it's y2 minus y1 divided by x2 minus x1. And in this case, I've got 2 minus 0.8, and that's in meters, because my y position is in meters. My time is 3 minus 2, or minus 1, and that's in seconds. And when I plug that into the calculator, I get 2 minus 0.8 gives me 1.2 divided by 2. This is in meters per second. Gives me 0.6 meters per second. So I can actually calculate the velocity. Okay, I can actually calculate the velocity. So now I can rewrite my equation. This b was actually 0. So now I have x is equal to 0.6 t. So the motion of this car in this situation can be described as 0.6 times time. So if I go in here and I put 1 second, I'm at 0.6 meters. If I put in 2 seconds, I'm at 1.2 meters. If I put in a half a second, I'm at 0.3 meters. So I can actually describe the motion of this car by looking at this position. That's exactly what we're doing. We're describing the motion in terms of a mathematical equation. Okay. A couple other things that we knew from algebra that they didn't tell you, right? I can look at a position versus time graph. And in this case, my position versus time graph is going to look like this. Okay? My position versus time graph. So the first thing that we know about this particular motion is it's not at a constant velocity. Okay? I don't have a straight line. So I'm not traveling at a constant velocity. I don't have a straight line. All right. But I can do some things. I can find the instantaneous velocity. So if I do this, I'm going to do these. And this is at 1 second, 2 seconds, 3 seconds. So I want to find the instantaneous velocity at 2 seconds. I have a graph. And if I remember my algebra, it says that I can look at my point at 2 seconds if I draw a line that is perpendicular to my curve. Okay, so I've got a line in here, and this is perpendicular, so I've got this reference point. That will give me my velocity at that point. That's how we do it mathematically. So I can calculate this. So I said, all right, so there's my, I can look at this. Okay, I got to give myself some reference points here. Let's make that. I make this. So they make this 1 and make that 2. So I can play with this. I'm going to have the rise over the run. So I can actually see where things are and make some approximations. So this one looks like, we'll call it 2.2. This one looks like it's at 1. This one we'll call it 2.5. And this one we'll call it 2 or 1.7. Okay. So my rise over my run, my rise is 2.2 minus 1. My run is 2.5 minus 1.7. And if I do that in there, I get 1.2. I get 0.8. And this is still in meters per second because this scale is in seconds. This scale is in meters. 0.2 divided by 0.8 gives me 1.5 meters per second. So if I had a radar gun, for those of you who play softball know that you can take a radar gun and actually calculate the speed. If I had a radar gun as my little car is going by, if I've got this on the little cart thing, I can look at the instantaneous speed and potentially be able to take the radar gun and figure out what the instantaneous speed is, and it's probably going to be about 1.5 meters per second. So I can do that, the instantaneous velocity. This also mathematically, if you want to know, most of you don't want to know, but you want to know, it's just the fun things that we do. This is actually the limit as time approaches 0 on my graph, my change in position versus my change in time. And this is instantaneous. Okay, so we can do an instantaneous velocity. We can do the exact same thing. If I were to change this to be an accelerate or a velocity versus time graph, I can do the exact same thing, and that would be an instantaneous acceleration. I can do the exact same thing. So I can have, most of the time what we deal with is what we refer to as an average, and that's what are going to be our average. This one, it refers to our average because we're taking that big picture approach. This is instantaneous where we're taking that kind of really, really small approach. You do have a homework problem, okay? You do have a homework problem that looks at it this way. Instead of looking at it curved like this on a curve or a graph, you're given an equation. And you're given an equation that says x is equal to, well, for grins and giggles, 3.5 times time plus 256, and it may be in t squared, but you're given an equation that looks like that. And it asks you to find the velocity between time is equal to 1 and time is equal to 1.5. You're going to plug in time, and you're going to figure this is 3.5 times 1 plus 2.56. And you're going to figure in the next one, 3.5 times 1.5 and plus 2.56. And you're going to get an answer. This is answer 1, and this is answer 2. And you're going to calculate the velocity. So I'm going to take answer 2 minus answer 1. And I'm going to have the difference in time. And I'm going to get a velocity. WebAssign is actually going to tell you to put it out to like 4 significant figures. So my value that I report is going to be something that looks like this. It's like 4 or 5 significant figures. Because then, this is part A. Part B says, all right, now I want to look at time at 1, and I want to look at time at 1.25. my time interval is getting smaller. Okay, my time interval is getting smaller. I'm going to follow the same procedure. I'm going to come up with an answer. C, the time interval is now like 1.0, the time is like 1.1. The time interval is getting smaller. What they're doing in WebAssign is they're doing the exact same thing here as what I'm doing now is I'm going to do the limit as t is approaching 0. As that time interval gets smaller and smaller and smaller, I'm now approaching what we call the instantaneous velocity. I'm now getting towards that instantaneous velocity. So it is very important that you do it to the proper significant figures when you actually work the problem. Okay? So we have a toolbox. We've started our toolbox. So far what we've got is a change in position with respect to time is going to equal velocity. I can rewrite this as x final minus x initial plus x final minus x initial is equal to velocity times time. Because my at x initial, t initial is equal to 0. Okay? At x initial, t initial is equal to 0. So I can rewrite this in terms of that. And so I can have x final is equal to my velocity times time plus x initial, remembering that that is a vector. But in this case, we're traveling only in the x direction, so life is fun. So that's one of my first equations that I can deal with. It's my first tool in my toolbox that I have. Okay. We also know, because we just did it, that velocity final minus velocity initial divided by time final minus time initial is equal to acceleration. Well, if my time at the initial spot is 0, I can rewrite my equation the same way, except now I get acceleration plus my initial velocity. So I have two equations that I can play with now. Two equations that I can play with. So let's look at this one. Let's look at a motion that we all know and love. So I've got a Cushman. Everybody knows what a Cushman is. It's a blunt-end little truck. My Cushman is at a stop sign. So my Cushman is a stop sign. And it's going to travel down the road for 5 seconds. And at the end of 5 seconds, the driver of the Cushman reads the speedometer and finds that he is traveling 10 meters per second. I want to know how far he traveled. No, I don't want to do that yet. We're not going to do that just yet. I'm not going to find out how far he traveled. Not just yet. But we want to know what was his acceleration. Okay? So he's at a stop sign. So what is his initial speed? 0. So there's something that I know that I didn't, that's not actually given to me in the problem, but I actually know that because of how they describe the problem. I'm at 0. So we've already figured out that the final velocity is going to equal the acceleration times time plus the initial velocity. We know the initial velocity is 0 because we're at a stop sign. We know time, and we know the final velocity. So I'm going to rearrange my equation. So my acceleration is going to equal the velocity divided by the time. I'm going to put in here my 10 meters per second. I'm dividing it by my time, 5 seconds. Okay? I get units of meters per second squared, which means I've done things, rearranged things correctly. My unit analysis helps me figure out that I've actually put it in the right spots. 10 divided by 5 tells me 2. The little Cushman was actually going at accelerating at 2 meters per second. The little Cushman was actually going fast. Okay. So now what we're going to do, I can also look at my average acceleration just a little bit. And if you actually want to get there, this is going on from, if you look at it in your text, you're going from equation 2.6, which is our velocity is equal to our initial velocity plus the acceleration. And we're going to do 2.7, because I can do an average velocity. I can say, in this case, it's not an arrow, this is my average velocity. Okay? It's not an arrow, this is average velocity, which means my velocity plus my initial velocity divided by 2. Just a regular good old average, right? Good old average. And this is valid for a constant acceleration. Okay? If I have a changing acceleration, life becomes really entertaining, but most of the time we're dealing with a constant acceleration. So I'm just dealing with that constant acceleration. If I want to look at my position, and we already figured this out, my position is velocity times time. I can put into my equation there, okay? I can put into my equation that change. So I get velocity plus v2 divided by 2 times time. Okay? Alrighty. So my change in position, or good old position, this could be my change in position, we'll keep it consistent, is equal to that right there, 1/2, we can rewrite it. I've got that. And let me see. So I'm going to go ahead and substitute this velocity right there. So now I get 1/2 velocity plus acceleration times time plus velocity times time. And now I end up with 1/2 2 initial velocities plus times time. I'm going to put my 1/2 through here. That gives me my initial velocity plus 1/2 acceleration. T times t is t squared. And I now have an equation that puts, this is in terms of velocity, acceleration, and time. This is in terms of position, acceleration, and time. So I have another tool in my toolkit. So now I can come back to my car. That's why I told you I didn't want to do distance first. When do we do distance now? Now I can figure out the distance. If I know the acceleration, how far did my little Cushman travel? Okay, distance is going to equal my initial velocity plus 1/2 the acceleration times time squared. What was my initial velocity? 0. So now I got my 1/2, and now I'm going to put my 2 meters per second squared, and we said we traveled it in 5 seconds, and my seconds have to be squared. Second squares are going to cancel, so I'm going to, and 1/2 of 2 is 1, so I'm going to end up at 25 meters. So I can figure out the distance that my car traveled. And if you want to play with algebra, okay, you want to play with algebra a little bit, you can actually show that v squared is equal to v initial squared plus 2a change in position. And this puts this in terms of acceleration, velocity, and position, and I've gotten rid of time. Okay? So I've got 3 equations here, and this is your kinematics toolkit. My kinematics, and kinematics means that we're looking at motion without regard to what it's what's causing the motion. So my change in position is going to equal my velocity times time. I have velocity is equal to initial velocity plus acceleration times time. I have velocity squared is equal to initial velocity squared plus 2 times the acceleration times my change in position. And I have my change in position is equal to my initial velocity times time plus 1/2 AT squared. And my error here is I forgot to write in time right there. Because t times that I did this part, forgot to carry through my time. So if you're going back to fix your notes, I have to have the time factor there. So this one is in terms of velocity, acceleration, and time. This one is in terms of velocity, acceleration, and position. This one is in terms of position, acceleration, and time. So depending on what you know will depend on which equation that you use. Okay, depending on what you know depends on which equation you'll use. And there'll be a lot of people say, well, how do I know which equation do I use? Well, if the problem says I have a horse, okay, if I have a horse, it's going to have an initial velocity of 1 meter per second. It's going to try to outrun the cheetah, so it's going to accelerate, okay? And it's going to travel a distance of 100 meters. And it's traveling at a distance of 100 meters, and it does it in a time, because we actually are watching it on the nature program, and we hit the stopwatch, and we're actually calculating the time, and it does it in 2.3 seconds. I want to know the acceleration. So I know x, I know time, and I want to know acceleration. This is known. This is known. This is unknown. That's my question. So I'm going to go to my toolkit. I'm going to look for the equation that has position, time, and acceleration. That one has position, time, and acceleration. I'm going to use that one. I'm not going to use this one because I don't have the final velocity. I'm not going to use this one because I don't have the final velocity. I don't know that. This one I have 2 that I don't know. I have 2 that I don't know. So we can do this. We can say, all right, I actually have an initial velocity. So I've got 100 meters is equal to my 1 meter per second times my 2.3 seconds plus 1/2 what I don't know times my 2.3 seconds squared. So I've got 100 minus 2.3 is equal to 2.3 squared divided by 2. 2.645 acceleration. This is in meters. And what I've got here is 1 over second squared. No, what I have here is second squared. So when I divide this, I get 100 minus 2.3. I get 97.7 meters divided by 2.645 seconds squared. My unit analysis tells me I've done it right. That says 36.9 meters per second squared. Now, because I actually pulled those numbers out of a hat, I don't know if that's reasonable or not. So I'm just letting you know, I just pulled those numbers right out of my hat. I don't know if that's reasonable or not. But that was the acceleration. So brains are full. We'll see you Wednesday.